So hello everybody, I'm here to present the work Faster Software Packet Processing on FPGA NICs with eBPF program warping. So first of all, I would like to thank all the co-authors of this work. This is a joint work by Axbryd, CNIT, NEC, and University of Roma Vergata. So let me give you a little bit of context. So it's widely acknowledged that due to different emerging paradigms like software-defined networking, network function virtualization, cloud-native networking, it is nowadays pretty common to implement a wide range of network functions in software and run them on top of general-purpose CPUs. Notable examples include layer 2 switching, layer 3 forwarding, firewall, network intrusion detection, and so on. Now, unfortunately, running software network functions on general-purpose servers and general-purpose CPUs require a significant amount of CPU resources, which significantly contribute to the overall infrastructure costs and energy consumption. Now, fortunately, on one side, the network traffic is still increasing every year for the introduction of new services and new technologies. But unfortunately, we have entered the post-Moore era, so it means that processors are not getting any faster. And this is the main reason why existing and emerging vendors are already commercializing a set of new network hardware accelerators named sometimes smart NICs or DPUs or IPUs, whatever. In the end, these devices are network interface cards with some additional hardware components that are specialized in execution of network workloads. So, how do we scale up the execution of generic software network function in the end host? So we may think that it's simple. We just push the software network function into the NIC. But this is a little bit, it's more complicated than we may think. And let's take a look at how these devices are designed. Now, of course, the architectural details may vary from vendor to vendor, of course. But from a high-level point of view, we have the following components. We have two interfaces, generally, one or more network ports and one host interface for communicating with the host system, like, for example, a PCI Express interface. One network data plane, which is usually a programmable ASIC processing unit and or an FPGA module. Then we have a processing clusters, which consists of generally general-purpose CPUs like ARM cores, RISC-V cores. And then we have a bank of dedicated accelerators that are responsible for the execution of functions like crypto, QoS, deep packet inspection, and so on. So, do we really have a solution? How do we execute software network function on this kind of architecture? So, the most obvious approach would be to leverage the typical SDN separation between the slow path and the fast path, the control plane and the data plane, and run the control logic of the program on the general purpose processing cluster and the packet processing program on the network data plane with some help from the dedicated accelerators. But this is not as easy, again, as it may seem. And actually, everything depends on which programming interface we have used to write our own programs. Now, what is the best approach for simplifying the overall network function development in the NIC while at the same time leveraging the specialized hardware architecture of these devices? Probably this question is not yet answered, but in the meantime, a new network programming interface has emerged from the Linux world. It is called eBPF, and it's getting a lot of attention from both the industry and the research community. And you can say that people are really looking to eBPF by simply observing the names of the early adopters and the huge number of research works related to this topic. So, it seems like eBPF is a good solution for programming our NIC. So, but how can we run an eBPF program on the NIC? So this is not easy at all. So one approach could be to use the general purpose processing cluster. Okay, from one hand, this approach would permit to run unmodified eBPF programs inside the NIC. But this approach would present a set of inefficiencies that are related to the fact that we are using general-purpose CPUs and also related to the overhead required to fully port the eBPF software framework into the NIC. A better approach in terms of performance would be to re-implement the eBPF program and run it on top of the programmable data plane and the dedicated accelerators. Now, This would be great in terms of performance, of course, but it would require an additional engineering effort because, of course, you have to readapt the program into the actual target architecture. But actually, things are even worse because this is not always possible. Because, for example, BPF is much more flexible than other programming abstractions. Okay, for example, P4. Now, P4 is great, again, but you can do more with eBPF with respect to P4. And it's not always granted that you are able to execute an eBPF program into the NIC. And lastly, each NIC is a different hardware platform. So we would need to re-implement every time for every different target architecture our program. And we would break this way one of the best features of eBPF, which is, of course, portability. So we really believe that if we want to run eBPF programs and modify the eBPF programs on the NIC, we really need to rethink about the internal architecture of the smart NIC. And this is what we have been doing for the last years. And in particular, in 2020, we published this work at USENIX ATC. The name was hXDP, Efficient Software Packet Processing on FPGA NICs. In this work, we proposed a full NIC design with a dedicated hardware block, including a very long instruction word processor that is specifically designed for the execution of a modified eBPF hXDP programs. Now, we proved that even if we have clock frequencies that are much lower, on the net FPGA we had, if I remember correctly, 150 megahertz, we managed to have performance that for some use cases was comparable with the performance that we obtained on a x86 software implementation. Now, we kept working on hXDP after conference, and we improved the design, of course, but we also ported the design from the net FPGA SUME to the Xilinx UltraScale Plus FPGA NICs, allowing higher clock frequency up to 250 megahertz, and in particular also enabling new features, like, for example, multi-processing, multi-core processing. Still, for some use cases, we were not able to reach the performance that we wanted to reach with a dedicated hardware. And this is what brings us here. So basically, the question is, can we do something smarter in order to get faster on the FPGA? And the answer is yes. And basically, in this work, we proved that with limited additional hardware resources and the help of a very smart compiler, we are able to boost the performance of unmodified eBPF hXDP programs up to a factor of 18x, for example, for the use case Vergata. So, but how is it possible? So let me give you a brief overview of how the program warping works. So on the left, we have a high-level description of all the entry points in which we can push an eBPF program into the kernel, namely the eBPF hooks. Now, needless to say that we are targeting the hXDP hook for our work because it's the hook that has least dependency on other kernel components and, of course, offers a good opportunity for hardware offloading. On the right, we have a very, very simple toy example that I'm going to use to show you how the eBPF program works. So basically, we are checking a few fields, the header length, the IP protocol, then we are constructing a key that we use to retrieve a status from an eBPF map. Then we take a forwarding decision according to the state that we retrieve from the map, and then we update a counter. Now, the original hXDP approach is the following one. So basically, we take the original program, we compile it with standard compilers, then we take the bytecode, and we adapt the eBPF bytecode into our hXDP instruction set, and then we run the program. So for every packet, we run the full program, all the instructions. As soon as we finish with one packet, we process the next packet. And this was the most reasonable approach for us because we didn't want to add any constraints on top of the constraints that a BPF programmer already has from the in-kernel verifier. But if we think a little bit about network programs, we may agree that even though you can write your eBPF program as you like, so in the end, most programs do a set of recurring operations, and in particular at the beginning of a program. So as highlighted here, for example, usually all network programs start with a more portion in which you parse the packet. So basically, you extract some fields from the packet, you verify a set of matching conditions, and you probably take some early verdict on the packet. For example, I don't care about IPv6 packet. Let's just drop it before doing anything else. OK. Then, after the parsing block, let's say, we always have a lookup key construction portion, in which basically you construct your key that you're going to use to retrieve some data from the eBPF maps. Now, this is the intuition of this work. If this initial part of the program happens before any other eBPF calls that produce an unpredictable output, this portion of the program depends only on the packet header, or on the packet in general, okay? So, assuming that we are able to build a software component able to understand all these matching rules at the beginning of the program, to understand how to parse the packet, and it understands how to reconstruct the program context in the point in which the map lookup is performed. And with the program context, I mean the content of the stack and the content of the register. And assuming that we have a hardware block specialized in the execution of this operation, and a hardware block who is able to push the program context into an hXDP executor, now we can completely skip the first part of the program, delegate the execution of this first part of the program to this specialized hardware block, and start exactly from the point in which we perform the map lookup. And of course, if the number of clock cycles required to execute the first portion of the program in hardware, in the specialized hardware, are significantly less than the number of clock cycles required by the software implementation, let's say, of the first part of the program, you get a performance improvement, a throughput improvement. Now, we know and we prove that actually this first part of the program can be easily and efficiently implemented in hardware. Because in the end, it's something like that match action table in the slide. Basically, you do some matches, you verify some fields, and then you decide what to do. You can drop the packet, transmit the packet, or in case of an execution branch in which you want to look up into a map, you can simply restore the context of the program and jump directly to the point in which you do the map lookup. And what I've just said is the general, it's how the program warping works. So let's recap a little bit. So we start from unmodified eBPF programs. We compile the program with standard eBPF compilers like LLVM. We get the standard eBPF bytecode. Now, we run our warp optimizer. The warp optimizers understand what are the warped instructions, so the instructions that can be executed by the warp engine. Automatically generates the configuration for the warp engine block, and then extract the unmodified instruction, so the remainder of the program, then push the remainder of the program into the hXDP execution environment, which in this case is, of course, hXDP, because this work can be seen as an extension to hXDP, of course. Now, all the packets that we are going to process in our architecture will first traverse the warp engine. It will be matched against the match action table I showed you before, and then, of course, they will enter the hXDP execution environment, starting from the context that is reconstructed and pushed by the warp engine. So let me give you a few details about the two main components of this architecture. So the warp optimizer is basically the compiler, okay? So it's this software component that is able to do what I just said. On the left, we have another example. This is even easier, but trust me, this algorithm works also with much more complicated use cases, but it would be impossible to show you how it works when I'm more complicated use cases. So basically, it does very few things. Just check the content of the Ethernet protocol. In case of IPv6, it drops the packet. In case of IPv4, it performs a lookup into the map. And all the other cases, it just pass the packet. Okay? So this algorithm starts by generating a control flow graph related to the program. Okay? So in this control flow graph, we can have different nodes. Well, first of all, we have the starting node. In this case, it's B1, the starting block. Then, of course, we have terminal nodes. A terminal node is a node in which we have either an exit or an eBPF call or a map lookup. Okay, so basically, when we reach this block, we need to emit a rule. when we reach a terminal node. Before reaching a terminal node, of course, we can traverse multiple middle nodes. Middle nodes can be matching nodes, or a matching node is a block portion in which we have a conditional jump with some packet value. Okay, if IP protocol is IPv4, jump to this branch. This is a matching node. A non-matching node is a block. Yes, it's a block in which you don't have a conditional jump. You have an unconditional jump, let's say. Okay, now, the algorithm starts like this. It initializes a set of internal variables to 0, like, for example, the current priority of the route that I'm going to emit, but it also set to 0 the list of fields that I'm going to read, the list of matching rules, the content of the registers, and the content of the stack. Everything is set to 0. And then it starts. Of course, it starts from the starting node. It performs a depth-first search and finds the first execution path. So in this case, the first execution path is B1, B2, and B6. And in this case, for each node, it understands if we are writing something in the stack, if we are reading something from the packet, it understands the matching rules. And in this case, it understands that there is one match field, which is basically from byte 12 to byte 13, which is the Ethernet protocol. And understand that this branch is triggered when we receive a packet with Ethernet protocol equal to IPv6. Now, when it reaches the terminal node, in this case B6, it emits the rule. And in this case, we have, with priority 0, that if we have a packet with Ethernet protocol, IPv6, we just drop the packet. Now, this is a recursive algorithm, so we go back to the first parent node, and we take another execution branch. In this case, the execution branch is B1, B2, B3, and B4. In this case, we end up in a terminal node in which we perform a map lookup. So in this case, the compiler understands how the program context is formed at the point in which we perform the lookup. And in particular, it understands that the program counter is equal to 34. Register 1 contains 0, immediate value. R2 contains -8, it's a pointer to the stack. Register 3 contains a byte in the packet. And in the stack, we have from byte 6 of the packet to byte 11 of the packet. Of course, soon it reaches the point in which we invoke the call, it emits a rule, a new rule, which is if you get a packet with Ethernet protocol IPv4, restore the context and jump at the point in which the program counter is 34. Now, again, recursive algorithm, we go back to the first parent, we take the last possible branch. This is an easy branch because basically this is the else branch, and in fact we emit a rule with a wildcard value on that match field, which is simply pass. So this is the beginning of our program. Can be represented as a match action table with this specific new restore context action. Now, let me give you a few details about the warp engine. So the actual hardware block that is going to implement what I just said. Now, this is a pipeline implementation of a fuse parsing unit and match action unit, which is similar to other ASIC switching technologies, but it's much easier in the end because of some optimization and simplification due to the co-design with the warp optimizer. So basically, we can see three main stages in this design. We have a field structure. This is a stage consisting of 12 substages in which we are able to extract up to 16 bytes from the packet and form a key. This key is used as lookup key for the next stage of the warp engine, which is the match action unit. It's exactly the match action table I showed you before. So we extract the key, we look up into this TCAM. And then, of course, if we have the hXDP verdict as actions like drop and transmit, we don't need anything else. But if the action associated to the TCAM key is restore context and jump there, of course, we're going to put in the register memory and the stack memory an indication of how to reconstruct the stack and the register at that point. Now, for all the packets that need to reach the final hXDP executor, of course, we need to traverse the context restoration unit, which is basically the piece of hardware that pushes inside the hXDP executor the context for that particular packet at that particular position in the code. Now, on the right, we have the last piece of the architecture, which is not a contribution of this paper, because this is basically hXDP. And in particular, this is the last version of hXDP, which was specifically extended in order to hook the warp engine into the executor. Now, without entering into other further architectural details, and probably I'm not even the best person in the team to talk about the FPGA design, let me summarize the main features of this warp engine. So basically, this is runtime programmable. It means that this pipeline can be reprogrammed at runtime according to the configuration produced by the warp optimizer. As I said before, this is a pipeline. It means that it never stalls. So it means that it is never a bottleneck for the overall execution of the program. Because here, the bottleneck is actually the hXDP executor. So the throughput is limited by the time required by the hXDP executor to complete the program. Third, for packets that need to be, let's say, either transmitted or dropped before the actual lookup, this warp engine completely replaces the software implementation. Instead, for the remaining packets, this piece of hardware basically restores the context, push the packet, and terminates the XDP program execution inside hXDP. Now, implementation. This is the overall picture. So basically, we have two main components, the compiler, the optimizer, and the NIC. Okay. The warp optimizer has been prototyped as a Python application that integrates also the hXDP compiler. The input of this software component is the standard eBPF bytecode, and the output is twofold. We have, on the one hand, we have the warp engine configuration, and on the other hand, we have the remaining of the program, let's say the unmodified instructions that need to be executed by the hXDP executor. The warp engine has been implemented on top of an Xilinx Alveo U50, clocked at 250 megahertz. And of course, here, our FPGA NICs includes both the warp optimizer and the hXDP executor. Evaluation. Evaluation took a lot of time, actually, for this work. And basically, we need to answer the following question. First of all, and this is probably the most complicated one, is the optimized program functionally equivalent to the original one? You don't have to think of the simple example that I showed you before. You need to think about a complex program. We have a lot of edge cases. So the first thing that we wanted to be sure about was, is the output of the optimizer functionally equivalent to the original program for all the use cases in our use case reference set? Second, how many instructions can we skip? Third, what is the throughput improvement? And last, how much do we pay in terms of new resources? Now, for different evaluations of the work, we used an emulator, a software emulator of our warp engine. Because basically, we had to compare the warp engine with an XDP implementation without the warp engine. So either we extend the kernel, or we had to do it in another way. And basically, we build a software emulator starting from the micro BPF implementation, the user space implementation of BPF. We extended that implementation in order to fully support XDP, and then in order to support the warp optimizer. This emulator takes an input, a pickup, which is the input trace, the input traffic, and generates 4 different pickup traces related to the 4 different eBPF verdicts: the transmit, the pass, abort, and drop. So basically, we can verify what we have in output for the warp engine and for the XDP executor without the warp engine. On the right, we have the set of reference use cases that we used in this work. We have the layer 2 ACL, the running example, stupid one, a dynamic NAT that we wrote, 2 examples in the kernel 3, the router and the TXT tunnel, and then Suricata, and then Catran. Catran is the Facebook load balancer, written with a BPF. Now, functional equivalence. To prove the functional equivalence, we enumerated all the program's control path in all the use cases. Then we synthetically generated a set of input traces that trigger all the different execution paths. And then, of course, we verified that the output was the same in case of the warp optimization and in case of no warp optimization. And of course, you can read the details in the paper. The functional equivalence is satisfied by our warp engine. Now, how many instructions can we skip? Of course, this depends on the particular use case. So what we did basically to see the impact of this is we counted the number of instructions without the optimization and the number of reduced instructions when we actually have the implementation. Then we divided this number and we saw the impact. For many use cases, we have an improvement factor greater than 50%, but at least we have 16.3% of improvement. Suricata is one of the use cases which work. Ah, okay, sorry, works really well. Okay, that's going to give you just a few, just about the additional hardware resources that we need. So basically, the combination of the hXDP and the warp engine takes less than 70% of all FPGAs resources. So we kept our original requirement, which was to be below 20%. And in terms of throughput, we have, that's Suricata, we have an average throughput of 308%. And for the other use cases, this is the average throughput improvement. 30% for the router, 28% for the tunnel, DNAT 23%, and Catran 131%. So sorry, it took me more than expected.